Hello everyone, so let's look at how we can calculate or relate the Kc value to the Kp value. And in this example, we're told that the Kc for the decomposition of ammonium hydrogen sulfide is 1.8 times 10 to the negative 4 at 25 degrees Celsius. Then we're asked to calculate the value of Kp. Alright, so we're given an equilibrium, so we're given ammonium hydrogen sulfide, which is a solid, and then it makes an equilibrium with ammonia and hydrogen sulfide. Alright, so the way that we relate Kc and Kp is we say Kc is equal to, Kp is equal to Kc RT to the power delta N, right? And if we look at that, that means we need to determine, we have Kc, we know what the gas constant is, and we know what the temperature is. So we need to determine what is the change in the number of moles for this, or the number of mole of gas for this reaction. So if we look at this reaction, on the reactant side, we do not have any mole of gas. So we have 0 mole gas on the reactant side, right? So it's 0 mole gas. Whereas on the product side, we have 1 mole of ammonia gas as a product, plus 1 mole of hydrogen sulfide gas that forms. Right, so that means we actually have 2 mole of product gas that forms. All right, and because we model it as perfect gases, it means we have 2 mole of gas mixture that forms. So that means that our delta N value, delta N, which is equal to the number of mole that we end up with minus the initial number of mole of gas, is equal to 2 mole of gas, 2 mole gas minus 0 mole gas, mole gas. All right, so that is then equal to a value of 2, right? So meaning that we end up with 2, so that's our final amount, and we started with 0, so that means the change in mole of gas for the reaction is 2, right? So that means that we can just plug it into the equation, right? So that we now have all the values that we need. So Kc is 1.8 times 10 to the negative 4, and then R is of course the ideal gas constant, but because we gases have partial pressures, and we usually work partial pressures in atmosphere, so we need to use R in the atmospheric universal gas constant, so that has a value of 0.082057, of course, and the units of that is liter atmosphere per mole per Kelvin, right? And let's actually put that in its own brackets, and then we need to multiply this by the temperature. Perhaps just first move it to the left a bit so that we have enough space to do that. We need to multiply that by the temperature, which is 25 degrees Celsius. We need to convert that to Kelvin. So that's 298.15 Kelvin. All right, and that all needs to be to the power delta N, so that is squared. And I eventually get this, so if you put that into your calculator, I get here a value of 0. Before I round, so before I rounded, I got 0.107739 and a bunch of numbers. And looking at what we got 2 significant figures, 1.8 and 25. So that means we round to 2 significant figures, so we get 0.11. Alright, and that makes sense. Our Kp is quite small because our Kc was quite small, right? Kc is 1.8 times 10 to the negative 4, and Kp is 0.11, which is also quite close to 1. So that is a very small value, indicating that this is it's not really a product or reactant favored equilibrium. It's difficult to really say it is close to 1, right? But now you've got the calculations. Important features here: keep your R in liter atmosphere per mole Kelvin. Why? Because you work in atmospheres for your products, so they're partial pressures. So when you work with Kp, you always use atmospheres. And to calculate delta N, you must look at what is our change in the number of mole of gas, or the amount of gas. All right. So those are the main features of this, and how we relate Kc and Kp for two reactions, or for the same equilibrium. All right. Good. Thank you for watching, and I'll see you in the next video.